I was sitting at my desk this morning just sipping my coffee and doing the usual routine.
Right, the daily grind.
Yeah, exactly. Dragging files into folders, saving documents, opening up photos. And it struck me how it all feels so automatic.
Almost ephemeral.
Yes, ephemeral. Like, it's just magic. You click save, and the data, it's just there, floating in the ether somewhere.
It really is the great illusion of modern computing, isn't it? I mean, we treat storage like this abstract, bottomless bucket where we just pour all of our digital lives.
You do.
We trust it implicitly.
Right, but we rarely stop to actually think about where that data lives because, unless you're strictly using solid-state drives, it is not magic. It's definitely not a cloud.
No, not at all.
It's physics, it is geometry, and quite often it's literally just spinning rust.
Spinning rust. That's the perfect term for it. And that's exactly where we're going today for our deep dive.
We're going right down to the metal.
We are. We're looking at the source material from Class 6 of a system administration course. Now, the syllabus frames this module as, let me check a lot of tricks, routine aspects of server management.
Which honestly sounds a little dry.
It sounds like chores.
Yeah, totally sounds like chores.
The reality of what's in these notes is so much more interesting. We're going way below the desktop interface today. We're talking about file system operations.
The actual mechanics of how a machine remembers things?
Exactly. This is the foundational layer. Because you can't really call yourself a system administrator if you don't understand what's happening on the physical metal when you type a command.
So, to set the stage for you listening at home, let's start with a hypothetical scenario. Let's say I hand you a brand new raw hard drive.
Okay.
I just took it out of the anti-static bag. It's got that fresh electronics smell.
Oh, I know that smell well.
Right. So I plug it into a computer. What happens?
Absolutely nothing.
Nothing at all. There's no welcome screen.
Nothing useful, anyway. That drive is what we call a blank slate.
Okay.
It has absolutely no organizing principle. It doesn't know what a file is. It has no concept of a folder or a directory. To that raw disk, your family photos or your operating system, they're meaningless magnetic pulses.
So it only knows its own physical anatomy.
Pretty much. It's an idiot savant of physics. It knows it has platters and it knows how to spin them.
Let's unpack that anatomy a bit because the source material describes disk drives, specifically these magnetic ones, as a sequential medium.
Right.
If we crack open that metal box with a screwdriver, which, side note, do not do that if you want to keep your data.
Definitely do not do that.
What are we actually looking at inside?
Picture a record player, but instead of just one vinyl record, imagine stacking a few of them on top of each other with a little bit of space in between.
Oh, okay. I can picture that.
Those are the platters. And just like a record player, there is an arm.
Yeah.
But this arm has multiple heads that slip in between those platters to read the data off the surfaces.
And the movement of that arm is key here.
Yeah. Crucial. Because unlike a vinyl record, which just has one long, continuous spiral groove from the outside in a hard disk, is organized into concentric circles.
Distinct rings.
Distinct rings. These are called tracks. And because you have multiple platters stacked up, if you look at the same track on every platter.
Like track 50 on the top one, track 50 on the middle one.
Exactly. That vertical stack forms a cylinder. So when we talk about disk geometry in the IT industry, we talk about CHS. That's cylinders, heads, and sectors.
There's a specific detail in the notes about that geometry that I found absolutely fascinating. It's this concept called zoned bit recording.
Oh yeah, that's a good one.
It sounds like something out of a sci-fi novel, but it's actually this really clever hack for efficiency.
It is. This is where the geometry actually gets fun. If you think about a circle, or let's say a pizza, if you're hungry.
I'm always hungry.
The crust is much longer than the center part, right?
Sure, yeah, just basic geometry. The outer perimeter is physically longer than the inner perimeter.
Well, in the really old days of computing, drives were super simple. They put the exact same amount of data on the outside track as they did on the inside track.
Oh, wow. So that means the data on the outside was really spread out.
It was a massive waste of space on the outer edge.
They just weren't packing it in tightly enough?
Exactly. But modern drives use zone bit recording to take advantage of all that extra real estate. There are actually more sectors, essentially more storage buckets, on the outside tracks of the disk than on the inside.
Okay, so they pack the data at the exact same density regardless of where it is on the platter.
Precisely. Because there's physically more room to fit them on the outside. And this optimizes for what is called constant angular velocity.
But constant angular velocity.
Right. The disk spins at a set speed, say 7,200 RPM. That speed is constant. It never, ever changes. But think about the read head for a second. When it's hovering on the outside edge, it is covering way more physical ground per second than when it's near the center.
Oh, right. It's like runners on a track. The person in the outside lane has to run further. So wait, let me think about this. If the head covers more ground per second, and there are more sectors packed into that ground.
Yeah.
Does that mean data on the outside of the disk is technically read faster?
You nailed it. That is the massive pro tip hidden in the physics here. The beginning of the disk, the outer edge, is literally the fastest part of the drive.
That's why.
That is usually where you want your operating system or your most frequently accessed data to live.
That is a huge insight for performance tuning. But there's a flip side to this physical reality, isn't there? Because the notes also mention performance metrics like seek time and latency.
Yeah, this is the constraint that we just can't code our way out of.
Yeah.
Seek time is how long it takes that mechanical arm to swing over to the right cylinder. It physically has to move.
It takes actual time.
Right. And latency is how long you have to wait for the spinning platter to rotate the specific sector under the head so it can be read.
It's all mechanical.
Milliseconds matter here. If your data is scattered all over the disk, that arm is just thrashing back and forth. Click where? Click where?
I remember that sound from older computers.
Yep. That's where your computer slows down.
Yeah.
You can't just download more platters. You are completely bound by the laws of physics.
It's just wild to think that every single time I open a file, there's this tiny mechanical ballet happening at 7,200 revolutions per minute inside my laptop.
It really is.
But okay, so we have this blank slate, this spinning metal. We obviously can't just write raw magnetic pulses ourselves. We have to organize it somehow.
And I just slice the pie. We need to tell the operating system how to treat this raw physical space. And that process is partitioning.
Right, partitioning. I feel like most people have seen this term when they're, installing Windows or Mac OS. It says create partition.
And it's usually a terrifying screen.
It is. You're always afraid you're going to accidentally delete everything.
And honestly, you should be afraid. But effectively, since the disk knows nothing, the operating system needs a map. The partition table is that map.
Okay.
It tells the system, okay, from sector 0 to sector 1000, that is partition 1. From 1001 to 5000, that's partition 2.
The notes mention a specific limitation here, though, that I found kind of surprising. A standard hard drive using the old master boot record or MBR standard usually maxes out at just 4 primary partitions.
Yeah.
That seems incredibly low for modern computing.
It is super low. It's a legacy leftover from the 1980s. The table literally only has enough bytes to list 4 entries. That's it.
So how do we get around that?
We use a trick called an extended partition.
Just a workaround.
Exactly. You take one of your 4 primary slots and you make it a container, basically a box. And inside that box, you can create logical drives.
Oh, like nesting dolls.
Like nesting dolls, perfect analogy. That's how we get dozens of partitions on a single physical disk, despite that ancient 4-partition limit.
Now, here is where it gets really interesting for me. The notes walk through using a command line tool like UFDisk to manipulate these partitions. And there's a slide in there titled Changes Are in Memory.
Yes.
It sounds like a warning, but you're telling me it's actually a safety feature.
It is the ultimate safety net. And this is a really crucial concept for anyone learning system administration. When you open a tool like UFDisk, and you start deleting partitions, resizing things, creating new layouts, you aren't actually touching the physical disk yet.
You're just editing a draft.
You are editing a copy of the partition table that lives in the computer's RAM.
Yeah.
In its memory. The physical disk hasn't changed a single bit.
So I could just mess everything up.
You could delete your entire operating system in the tool, wipe out the boot sector, remove every trace of your data, and as long as you don't save it, you're completely fine.
So that's the panic button the source material mentions?
Yes. If you realize you've made a terrible mistake, say you accidentally deleted the partition that has your PhD thesis on it.
Oh, no.
You just hit Q for quit or hit Control-C. The program terminates, the memory's wiped clean, and your disk remains completely untouched. It's literally like waking up from a bad dream.
But the moment you hit W?
The W command. That stands for write.
Right.
The moment you hit enter on W, the application calls the kernel and basically says, make it so. It flushes that draft table from memory directly to the physical disk. the deal is done.
No going back.
If you messed up, that is when the data loss happens.
Talk about high stakes. I can totally see why the syllabus emphasizes hands-on learning, but also heavily emphasizes safety.
Yeah, you have to be careful.
Which actually brings up a great question posed in the notes. How do students actually practice this? I mean, I wouldn't want to practice partitioning on my main laptop hard drive. One wrong W and I'm toast.
It's a classic problem in IT education, right?
Yeah.
How do you teach dangerous things safely?
You can't just buy everyone 10 spare hard drives to destroy.
No, the budgets wouldn't allow that. The solution in this class is really clever, though. It uses what's called a virtual disk.
A virtual disk? Now, is that like a cloud drive? Like Dropbox or something?
Yeah. No. Much more local than that. And much deeper in the system. Linux allows you to take a regular file, just a big empty file sitting in a folder, and trick the operating system into treating it like a physical piece of hardware.
Wait, so a file acting like a piece of hardware, like a purely software simulation?
Precisely. The notes give the recipe, and it's surprisingly simple to do. First, you use a command called fallocate.
Okay.
Specifically, the notes say fallocate -L3G/root/data disk.
Let me decode that for a second. So fallocate allocates file space. The -L3G means a length of 3 gigabytes, and /root/data disk is just the name and location.
You got it.
So at this point, we just created a 3 gigabyte block of zeros on the hard drive.
Right, just a big empty dumb file. If you opened it in a text editor, it would be completely boring.
Just blank.
Yeah. But here's the magic trick. You then use a command called looseUp. That stands for loop setup. You map that boring file to a loop device like /dev/loop0.
And once you do that, the computer stops seeing a file and starts seeing a block device.
Yes. The operating system essentially hallucinates that /dev/loop0 is a real physical hard drive plugged into a port.
That is so cool.
It is. You can run an fdisk on it, you can format it, you can partition it, you can completely corrupt it. And if you completely destroy it...
You just delete the data disk file and make a new one?
Exactly. Your actual physical hard drive, the one running your computer, is perfectly safe.
That is such a brilliant way to learn. It really separates the logical concept of a disk from the physical reality. It's a sandbox in the truest sense of the word.
And that separation is really key to the whole philosophy of Linux file systems, which actually brings us to the next big hurdle for people coming from a Windows or a Mac background, and that's mounting.
Oh man, mounting. This always trips people up. Coming from Windows, I'm used to plugging in a USB drive and immediately seeing E drive or F drive pop up.
Right, little independent islands of data.
Exactly.
Yeah.
But Linux doesn't do letters, does it?
No letters at all. Windows uses drive letters, which is a bit of a disconnected way of viewing your storage. You have C, D, E. They are completely separate hierarchies.
Yeah.
But Linux uses a tree.
A tree?
A single unified hierarchy starting at root, which is represented by just a /.
One tree to rule them all. So if I plug in a new hard drive on Linux, where does it go if it doesn't get a letter?
It goes literally wherever you want it to go. That is what mounting is.
Okay.
The notes define it perfectly. They say it's the process of adding the new file system into the existing file system by joining it to a mount point.
And a mount point sounds really technical, but isn't it just a folder?
It's literally just an empty directory.
Yeah.
Let's say you have a folder called /data. Currently, it's empty.
Yeah.
You can tell the system, hey, take this new hard drive partition and attach it to /data.
Okay.
Suddenly, when you open that folder, you aren't looking at your main drive anymore. You're looking at the contents of that new partition.
It's like opening a door in your hallway. A door that usually just leads to a coat closet, but you've rigged it so it magically opens into a completely different building.
That is a perfect analogy. And you can mount things anywhere in that tree. You can mount a drive to your home folder. You can mount it to a temporary folder.
So the user doesn't necessarily even know which physical disk they are writing to.
They don't need to. They just see the directory tree. It totally abstracts the hardware away from the user experience.
But how does the computer know where to put these things when it wakes up? I mean, I don't want to have to manually mount my drives every single time I reboot my server.
Right, that would be a nightmare.
Yeah.
That is handled by a configuration file mentioned in the notes called /etc/ifstab or sometimes iftab. It's basically the blueprint.
The blueprint for the doors.
Exactly. When Linux boots up, it reads that file to know exactly which stores to open and which physical drives to connect to them automatically.
All right, so we've got our disk, we've partitioned it safely, we've mounted it, we start saving files. I name a file mynotes.txt. You name a file projectplan.doc.
Simple enough.
But here is where this deep dive gets really mind-bending for me. The expert in the notes explicitly says names are an illusion.
Yes. This is the big aha moment of the course. We humans are obsessed with names. We absolutely need meaningful labels to find our things.
Of course we do.
But the computer, the file system itself, it's not care about mynotes.txt. It doesn't care about resume.pdf. That name is literally just metadata kept around for your convenience.
So if the computer doesn't use the name to find the data on the disk, what does it use?
It uses numbers,
Right.
specifically an index number. We call it an inode.
An inode. Okay, this is a term I hear tossed around by sysadmins a lot, usually when something is horribly broken.
Very true. Every single file on a Linux system is identified by a unique inode number. The notes show this really clearly. If you run the command -i, the I stands for inode, you stop seeing just names.
What do you see?
You see things like 1308645, anaconda-ks.cfg.
So that number, 1308645, that is the real identity of the file.
That is the file. That number points to a data structure on the disk that says, okay, file 1308645 lives on these specific sectors, it has these specific permissions, and it is owned by this specific user.
And the file name anaconda-ks.cfg is just a sticky note pointing to number 1308645.
Exactly.
This completely changes how I think about file organization. Because if the name is just a label pointing to a number, can you have two labels pointing to the exact same number?
That is a brilliant question. And the answer is absolutely yes. This is what we call a hard link.
A hard link. Okay, walk me through how that actually works in practice.
Imagine a physical person standing in a room. That person is the inode. They are the actual data, the flesh and blood. Now imagine putting a name tag on them that says Dave.
Okay, Dave is the file name.
Right. Now imagine sticking a second name tag on that exact same person's chest that says boss.
Two name tags, one person.
Exactly. If I call out Dave, that person responds. If I call out boss, the exact same person responds. That is a hard link. You use the command ln to create one. The notes give a specific example for this. ln setupserver.txt sas.dat.
So setupserver.txt and sas.dat are two completely different file names, but they point to the exact same inode number under the hood.
Correct. And here is the major implication of that.
Yeah.
If you modify sas.dat maybe your allowance, maybe you open it up and add a line of text when you later open setupaserver.txt, that new line is there.
Because it's literally the same file.
It's the same physical sectors on the disk. You aren't copying the data at all. You're just adding a new door to access it.
Now, here is the trickiest part for me. What happens if I delete setupaserver.txt? Does the underlying data disappear?
No. And this is exactly why understanding inodes is so critical. If you delete one file name, you are just ripping off one of the name tags.
Oh.
The inode is still standing there in the room because its link count hasn't dropped to 0.
The system keeps account of the name tags.
It does. Every inode tracks exactly how many file names are currently pointing to it. The data only gets actually deleted, meaning the space is marked as free when the very last name tag is removed.
That is fascinating. It's almost like a built-in backup mechanism. As long as something somewhere points to that inode, the data survives.
Precisely. But there is a major limitation you need to know about hard links. They have to be on the same partition.
Why is that?
Because you can't have an inode on your C drive equivalent and a hard link to it on your D drive. They are different universes. They have different sets of inode numbers. Inode 500 on one drive is not inode 500 on the other drive.
Okay, that makes total sense. So what if I do want to link to a file on a completely different drive? Or what if I just want a shortcut that feels a little less permanent, like the shortcuts I'm used to on my Windows desktop?
For that, you use a symbolic link or a symlink. This is much closer to the standard shortcut users already know.
And how does a symlink differ technically from the hard link we just talked about?
A symlink doesn't point to the inode number. It points to the path.
The path, like the file address.
Yes. Think of it like a signpost. A hard link is a name tag stuck directly on the person. A symlink is just a sign on the hallway wall that says, go to room 12 to find Dave.
Okay, I clearly see the distinction now.
The command for that is nnn-s. The S stands for symbolic. Now consider the danger here. If Dave moves out of room 12.
If you delete the original file.
Right. The sign is still hanging on the wall.
But it points to an empty room.
Exactly. The link is broken. The notes explicitly show this happening. If you try to read a broken symlink, you get an error. No such file or directory.
Right.
The link itself exists, but its target is completely gone. With a hard link, if you deleted the original name, the data would still be accessible via the other name. But with a symlink, if you delete the target, the link becomes useless.
You know, this distinction between a hard link and a symlink, it really separates the casual user from the true sysadmin.
It really does.
The casual user just sees two desktop icons that look exactly the same, but the admin knows one is a direct pointer to the physical data and the other is just a flimsy signpost.
And that knowledge is absolutely crucial when things go horribly wrong. Which brings us to the ouch factor mentioned in the slides.
Yeah, I saw that on the final slide for the lab material. It's a big red stamp that just says OUCH. It felt extremely ominous.
It's funny, but it's very real. System administration is basically a contact sport. When you are messing around with partition tables and inodes, your mistakes are painful. You can easily lose data.
And the ultimate nightmare scenario mentioned in the notes is FLISC, file system check.
FLISC, yeah. It's the tool you run when a file system is corrupted. Say the power failed while you were writing to that partition table we talked about.
And what happens when FLISC tries to fix things? I mean, it sounds like it should be a helpful utility.
It definitely tries to be, but often severe corruption destroys the directory structure itself. It destroys the file names. Because remember, file names are just a list of name tags.
Right.
If that list gets scrambled, SEC scans the raw disk and finds these orphaned chains of data. It knows they are valid files because they still have intact inodes, but it has absolutely no idea what they were called or where they belonged in the tree.
Oh, man. So you stop seeing familyphoto.jpg and resume.doc.
And you start seeing files named simply by the raw inode numbers, like literally file #1308645, dumped into a massive folder called lost plus found.
That is brutal.
It is the exact moment where the abstraction breaks down completely.
Yeah.
You aren't dealing with your neatly organized life anymore. You are dealing with raw database entries. You have to open them up one by one manually to figure out what they even are.
That sounds like an absolute horror movie for a sysadmin, just sifting through thousands of numbered files, desperately trying to find your main database config file.
It really is. It's the moment you realize that names were always just a convenience and the inode is the only real truth on the disk. It brutally exposes the fragility of the whole system.
It really makes you appreciate the layers of software that keep us comfortable every day. I mean, we trust our entire digital lives to these systems. We just assume our files are permanent physical things, permanently named what we named them.
But they really aren't.
No. As we've learned today, they are literally just scattered magnetic sectors on a spinning metal platter tied together by a very fragile list of numbers.
That's right. If that list breaks, if your inode table gets corrupted, your precious data becomes nothing more than digital noise. It's a very powerful reminder of why we do backups and why we treat that write command in fdisk with so much respect.
Well, on that slightly terrifying but incredibly illuminating note, we are going to wrap up this deep dive into file system operations. It certainly makes me look at my save button with a bit more reverence today.
Before you go, though, here's a quick challenge for you listeners. Next time you open a terminal on a Linux machine or even a Mac, since it's Unix-based, under the hood, just type -i in your Documents folder.
Look at the numbers.
Yeah. See the matrix behind the names?
I am absolutely doing that as soon as we finish recording here. Thanks for listening, everyone. Keep those partitions safe, watch out for those hard links, and we will see you on the next deep dive.
Safe computing out there.